Hello and welcome back to another episode of Lucas Lack 124. Today we're going to be talking about electrostatic actuators, more specifically HASEL electrostatic actuators, and we'll get into a bit of more of what those are later in the video, but for now I'm going to give a bit of an overview of what an electrostatic actuator is and how it works. So in their most common form, electrostatic actuators are a subfield of microelectromechanical systems, or MEMS devices, electromechanical systems built on and using the same technologies as the integrated circuits that they're electrically attached to. They are incredibly small and operate due to the attractive electrostatic force generated between two dielectric plates when energy is passed through. Dielectric substances become polarized as electricity flows through them, allowing the whole thing to occur. Often, the plates are attached to a spring-like cantilever arm or linkage in order to return the actuator to an equilibrium position after each actuation. Various configurations, arrangements, and arrays of this two-plate design have been developed and employed. Examples of this include microscopic motors and actuators, such as the cantilever actuator, the torsional actuator, the comb drive, rotary micromotors, and scratch drive actuators, and you can see those all now. But this isn't the end of the usefulness of the electrostatic actuator. Electrostatic actuators as a concept, given sufficient power input, can be scaled up to macroscopic sizes. This is where they become useful in macroscopic robotics and biomedical applications. At larger scales, power requirements are greatly increased, but so too are the effectiveness of the devices, such as the actual effective strain that they can output. Using the same previously discussed principle of attraction of dielectric substances, hydraulically amplified self-healing electrostatic actuators, or HASEL actuators for short, combine flexible substrates with dielectric hydraulic fluid in order to amplify deformations due to contraction of charged dielectric surfaces. Local redistribution of liquid dielectric results in a shape change of the structure. A unique element of these actuators is their ability to undergo high amounts of deformation, significantly higher than traditional solid substrate actuators, without resulting in permanent deformation or failure of the system. If the dielectric fluid within a HASEL ever becomes fully conducting, it can redistribute, and in this way returns to an insulating state. This makes them ideal for haptic feedback systems, high deformation actuation, and applications which require the ability to handle repeated instances of high stress and strain. These systems typically require 5 to 15 kilovolts to operate and the levels of deformation required by researchers. However, variances in the dielectric elastomer choice used can result in a range of resultant stress outputs and voltage requirements for actuation. Commonly, HASEL actuators use hydrogel or aluminum for dielectric construction, but there are many materials which have been explored at the MEMS level that have not yet been tested extensively at the macroscopic scales of HASEL actuators. Just as with their microscopic counterparts, HASEL systems come in many shapes and sizes. However, the specific focus of this video is on the viability of HASEL actuators as artificial muscle tissue. In order to transition from general information about HASELs to this specific topic, we need to talk about a specific type of HASEL that's commonly used in the creation of artificial muscle tissues for robotics: the planar HASEL actuator. As you might have guessed, planar HASEL actuators only allow deformation along a specific plane. In this way, the entirety of the potential created as a result of the actuation of the system can be directed to elongation along a specific path. Linear planar HASEL actuators take this a step further and only positively deform linear along a single direction. In order to be used as artificial muscle tissue, a pre-actuation homeostatic position must be built into the actuator in the form of an arched, well-filled dielectric sac. The shape of the sac, in combination with its internal, highly incompressible fluid insides, and resistance to deformation in all but a single direction, result in the ability of the system to support weight without deforming when electricity is not applied. Due to the way in which they operate, linear planar HASEL actuators are highly controllable, with feedback systems that are able to be implemented to measure the resistance of the system and then use that to detect and adjust the level of actuation of the system. They are also highly effective at achieving the high strain required of an artificial muscle tissue, and are able to actuate proportionately more than many similar technologies in the same field, such as other types of HASEL actuators. They are highly scalable, meaning that they can achieve impressive outputs. However, the current limitation of the technology is the operational lifespan of a HASEL, the specific type of HASEL to be more exact, the linear planar HASEL. They don't really last nearly as long as real muscle tissues, resulting in a low adoption rate in robotics and primarily being relegated to demonstrations at this time. In congruence with this, several researchers have demonstrated the ability of similar, more developed versions of the general HASEL actuator concept to act as highly controllable, moderately high actuation robotic components. These include manipulators and actuators for the movement of robotic limbs. Moreover, there is a company selling HASEL actuators for robotic applications. There are few issues of ethical concern with such an undeveloped and largely passive technology. Production is small enough so as to create a negligible environmental impact, despite the limited lifespan of the actuators. The limited lifespan as a possible safety and reliability concern is being addressed through further research. Research is also going into making the devices easier and cheaper to reproduce. As dielectrically driven robotics components, their only major issue is the fact that they require quite high operating voltages. This is being addressed through proper construction of the devices, and possibly in the future will also be addressed by using some of those MEMS materials talked about before. I hope you've enjoyed this incredibly dense video on dielectric actuators. I certainly know that this has been an interesting research experience for me and will possibly result in some future research of my own. Thanks for watching, and I'll see you next time.